In our next section, we're going to talk about the IBGP versus eBGP peering rules and how this specifically changes what the loop prevention mechanism is, how we establish the actual peerings, things like the next hop processing as well, and specifically why we even care about the next hop in BGP, because ultimately that's going to be used for the forwarding of traffic. Now, as we saw in our previous section with our packet capture, we saw that in an IBGP packet, the default time to live is 255, which implies that the neighbors do not have to be directly connected as long as IGP reachability exists. So again, in most typical design cases, you would see that the IBGP peers connect via their loopbacks, because this is going to allow us to reroute around a failure in the transit network by using our IGP. So again, for example, if we were to have two edge routers, let's say that our edge routers are router 10 and router 9, and then these are routing us out to our internet links. So let's say we have ISP-A and we have ISP-B over here, and we're doing eBGP peerings to them. We may want to form an IBGP peering between the neighbors in order to exchange the updates. And this is assuming then that we have an IGP in the middle that's going to provide them transport. Now, there are some design cases where BGP will be used as the internal routing protocol, but those are very few and far between. The reason why we'll see has to do with the advertisement rules of eBGP versus IBGP. Now, one technically valid design would be to configure every single router in its own separate BGP AS, and then we would peer based on the physical topology. Now, we'll talk about what are some valid cases where you actually might want to do that, but they're normally corner case designs. Typically, you would just peer IBGP multi-hop between your own internal peers, and then either have full reachability internally. You could do like a default route to the edge. You could do MPLS in the core, and we'll see that this is going to be required, the peering between the loopbacks for the specific application of MPLS layer 3 VPNs. Now, in the case of eBGP peerings, the time to live is 1. So this means that normally the device is directly connected. If for some reason they are not directly connected, then we need to increment the TTL. Now, there's a couple different ways that we can do this. One is simply by saying change the time to live to this value, which would be the eBGP multi-hop command. Or there's another one here that is the TTL security. Now, the second one is the better implementation within current designs. And we'll talk about this when we talk about control plane security and the difference between doing authentication versus doing some other logic checks in the control plane. Because typically when you run a BGP peering, you always want to authenticate it. The reason why is that there are some attacks that you can do against BGP based on guessing the TCP sequence number and then causing the router to generate a TCP reset. So the idea is that if I'm somewhere in the network, and I don't even have to be in the same network, I just have to have transport to the router. So let's say that I do a trace route through the internet and I figure out that this is your edge router, and your edge router has the IP address 155.1.9.9, and this is the address that they're using to peer through BGP. Me as an attacker, I can simply pound this address over and over and over with TCP reset messages at port 179 and try to guess the correct sequence number. And there is some sort of statistical way that it is possible to do that. So the router is subject to this attack if the session is not authenticated or if we don't configure TTL security. So the end result of this is basically if you get the router to reset the session, you drop all of the routes and then you drop all the data planes. So it's just a basic DOS against the router, simply that it loses its reachability information. But the idea of doing TTL security is that the neighbor checks when the packet comes in what the minimum TTL is, which means that normally this is enforcing that the router must be one hop away. So let's take a look at this here specifically in our case, where we were doing a peering between a router 4 and router 5, and specifically router 4 is configured in AS 4.4, router 5 is configured in AS 5.5, and then router 4 was doing packet capture in the control plane when the BGP updates were actually coming in, or the BGP messages. So if we look at the result of router 4, actually let's do this. Let's say on 4 that I'm going to limit these messages because there's other stuff here that I technically don't need to capture. Let's do this. Let's say access list, IP access list extended BGP is going to permit TCP any equal to 179 and permit TCP any equal to 179 any. Okay, so in both directions. Then we'll say monitor capture 1 stop. Monitor capture 1 access list is BGP. Then monitor capture 1 start. And then 1 buffer, or I think it's just clear. There we go. Okay, then let's say clear IP BGP star. So that's going to restart the sessions between the neighbors. So that we have the new eBGP peering. Okay, let's go ahead and export this. Let's say monitor capture 1 export to TFTP. Okay, my Wireshark machine there is, we'll say that this is r4.ebgp.pcap. And specifically, we want to see what is happening in the frames when they come in and out between router 4 and router 5. Okay, so here's the session. We can see that was the fin. The fin was basically when I cleared the session, it caused them to drop it, and then they're now doing the new handshake. So this was the clear BGP hard, then this is the new open message. Now, if we look at the specific information, so let's look at like the keep alive. Okay, a keep alive specifically in BGP means that you're already converged because you don't generate keep alive until you're done sending update messages. Now, in this case, I haven't advertised anything yet into BGP, so once the peering comes up, then they're going to start to send keep alives to each other. But specifically, if we look inside the packet and inside the IP header, it says the time to live value is 1, which again, that's the default for eBGP. Now, again, we could change this if we were to go to the process, and let's say under router BGP 4.4, let's do show run section BGP. Let's say that for this neighbor, router 5, they are an eBGP multi-hop neighbor, and let's say their TTL is 100. Then let's clear the BGP session again, and then let's re-export the capture, and we should see this change now in the new open message between the two of them. So here's the open message from 5 to 4, and then we get a response from 4 back to 5, and it should show us here now the TTL is 100. Okay, so that's all the command is doing. eBGP multi-hop is just changing the time to live in the IP packet. Now, the TTL security is a little bit different, where TTL security is going to be the reverse logic of this. So let's now say on router 4, when we show run section BGP, that we're not doing eBGP multi-hop because these commands, they are mutually exclusive. You can only use one at a time. Where we're going to say the neighbor has TTL security configured and the number of hops that they are away is just 1. So we're saying the neighbor must be directly connected on the eBGP link. And let's do the same thing on router 5. You need to do this on both sides in order for them to agree upon it. The TTL security is 1. Okay, and we can see here we got a notification here. This is router 4 tearing the session down because there was a violation of the TTL security. Okay, we're going to say that they're 1 hop away. Now the session comes back up. If we now look at the export of the capture, what we should see that has changed here is all the way at the bottom, our last session that we just established. When 4 goes to send a BGP message to 5, notice what the TTL is now. The TTL is 255. The basic logic of this is that I can now use the time to live value in order to figure out how many routers did the packet forward through before the packet got to me. So think of it like this. Let's say that we're trying to do an attack on router 5, but we can't insert ourselves physically into this link. So let's say that we're somewhere in the IP cloud, we're somewhere in the internet, and we're trying to attack router 4 in order to get it to drop the session from router 5. Well, one of the things that we would need to do to successfully do this attack is we would need to spoof router 5's address. But that portion is arbitrary. It's trivial to do that because I can simply trace to a destination and I could trace from different points of the internet and look at what's the address that's on that link. And you could see this if you do this on like one of the route servers. So for example, if we go back to routeviews.org, rviews, and let's say that we trace www.google.com, okay, and trace, well, let's not say them because they were using IPv6. Cisco.com. Basically, what this is showing us here is what are the specific IP addresses that, in this case, they're actually also using IPv6. Let's try to, let me force this to use IPv4. Or actually, let me just look at it from a different route server. Let's say AT&T. Rviews. Trace route, www.cisco.com. This is actually a Juniper router, this one. And actually, it's still using IPv6. Let me go back to the other one. Trace IPv4, I need to say. There we go, www.cisco.com. Okay, so notice here what's happening specifically in the path. What it's showing me is what are the providers that are going through, what are their AS numbers, and then also what are the specific addresses of the links. Now, most providers, in most practical cases, they don't filter out ICMP unreachable because it makes troubleshooting the network way too complicated. So we will be able to discover what are the addresses that the routers are peering with, because you would assume that if we trace through the link connecting us, and then you reply to whoever did the trace route, you're going to source that from the address that I'm using to peer with. Because we're eBGP neighbors, look at these addresses. Most of these are /31s or /32s. So it's trivial to figure out then what is the address that I would need to spoof this from. And then I can simply send the TCP resets to the router and try to guess the sequence number. So eventually, if you let this attack run, it will find the correct number, and the end result is that router 4 would generate a notification message and drop the session. Now, there's another potential issue here. You could say, well, why don't you just authenticate the session? That would be a simple solution, right? So let's use a password between router 4 and router 5. And we'll show this a little bit later when we talk about more security details, that if you use an MD5 hash, the problem now becomes someone can DOS your CPU by sending you all sorts of frames that are malformed because you need to hash each of them. So they came up with a simpler solution to say, when the packet comes in, look at what the TTL was that it came in on. If I am supposed to be directly connected to that peer, it means that the TTL should be 255. Because if it was routed through someone else in the meantime, they would have decremented the TTL. So it's basically using a reverse logic to say, set the TTL as high as possible, and then based on the number of hops away that they're allowed to be, the TTL is going to have a lower floor that I will not accept the packet below. So in this case, if the packet was received with a TTL of 254, it means that they're more than one hop away, and then it would get discarded. So the idea is that we want to throw it away before the control plane even sees it. We don't want the packet to get to the general purpose CPU. So that's why they give you the two options in order to do this in the peering. But again, the main point is that these are mutually exclusive. You would not say eBGP multi-hop and TTL security at the same time. I'm pretty sure the parser will just argue with you and tell you that you can't do it. Now, you can make them more than one hop away. And in the case that the peers are technically not multi-hop, but they might be peering on their loopbacks. So let's say, for example, that we had a case where router 4 and router 5, they're connected over the DMVPN cloud, and then they're also connected over this direct link. So if we were to go to router 4 and we were to say, what is the route to router 5's loopback? Show IP route 151.55. we see we have multiple paths. Okay, one of them is on the underlay interface for DMVPN, and one of them is on the point-to-point link. But if we were to do a trace here, we see that we do ECMP. So some of the packets go directly to 5, some of them go to these are two different links. But let's say that we were doing this. So if we show run section BGP, let's say instead, and actually let's just remove the BGP process, that'll be the easiest. No router BGP 4.4, and same thing on the other side. No router BGP 5.5. Let's start this over. Okay, so let's say router BGP 5. The neighbor is 151.4.4. The remote AS is 4. And the update source is going to be my loopback. Okay, we do the same thing on router 4. Router BGP 4. The neighbor is 151.5.5. The remote AS is 5. So they're an eBGP neighbor. And the update source is the loopback. If we now clear, or actually say monitor capture 1 clear, and clear IPBGP star, let's go ahead and export the capture again. So let's say that this is R4 to R5 loopback eBGP. And let's look at what the results of the capture are now. It's actually nothing. And let me take router 1 out of the equation here because it's still trying to run BGP to the other router. So let's clear the buffer, clear the BGP session, and then export. So the capture is empty. Why would the capture be empty here? The issue is that with eBGP, if the neighbor is not directly connected, we don't initiate the session to them unless the time to live is artificially high. So in the case of eBGP multi-hop or TTL security, you can set the number of hops away that they are, which means that you initiate the session. But in this particular case, I'm peering between 4 and 5's loopback. They're eBGP neighbors. I did set the update source on both sides, but they'll never establish a peering. This is because we either need to increase the time to live or tell them to disable this connected check. So this is the other option where we're technically not increasing the TTL. We're just saying under the process for this particular neighbor, 151.5.5, disable the connected check, which means that we should be able to send them a SYN, which means that they should reply back with SYNAC, and we should see that they should form the session. And I think we need to say this on both sides. Neighbor 151.4.4, disable connected check. Okay, now the neighbor's up. If we go to router 4 and export our capture again, let's look at the actual header format and see if anything changed. And we want to see just in any of these messages. So let's say the initial SYN, if we look at in the IP header, notice what's still there. The time to live is still 1. Because in this case, when I'm routing the packet to the loopback, the packet goes into 5 forwards it to the loopback, it doesn't decrement the TTL. The router technically does not decrement TTL until it goes to forwarded egress on a new link. Because you don't decrement the TTL until you rebuild the frame. And when you move the packet between interfaces, then you need to rebuild it. In this case, it's going to the local control plane process. It doesn't actually route to the loopback. The loopback is a logical construct inside of the router that it says the packet came in, it's for my local process, send it to the BGP code. So even though they're technically multiple hops away from like a trace route point of view, so from router 4, if we were to say to trace to 151.5.5, we do see 2 hops here. Well, technically we don't see 2 hops. We see just the connected link and then the packet forwards to the loopback. Now, why would you even want to do this to begin with? Really, the result of this is going to be based on the advertisement and based on the next hop value. So we're going to come back to this in a couple minutes here and talk about why would you want to peer between two eBGP neighbors and use the loopback when you're multiple connected on multiple links. But again, the main point of this is that when you're doing the eBGP peers, the TTL is 1 unless you manually increase it. You can manually increase it with eBGP multi-hop or TTL security, or in the case you're peering with the loopbacks and they are directly connected, then you could disable the connected check. Okay, the next difference between them, between iBGP and eBGP, is going to be the loop prevention. In the case of iBGP, the loop prevention is very simple. The idea is that if I learn a route from an iBGP neighbor, I won't advertise it to another iBGP neighbor. So this means I could never loop the advertisement because I'm never sending it to begin with. This has 3 different implications in the iBGP design. This means that the routers either need to have a full mesh of peerings, or they need to use some sort of exception, which is either route reflection or confederation. Now, we're going to get into both of these in much more detail. Actually, all 3 designs we're going to get into in much more detail, because there are pros and cons of all 3. There are cases where you would want a full iBGP mesh, and there are other cases where you don't need it and you can just use either route reflection or confederation. In my personal opinion, there's no need for confederation. I've rarely seen it implemented in production. Almost everybody does route reflection. It's a simpler design. But in reality, route reflection and confederation is the same exact thing. It's a different implementation in order to get to the same goal, which is to reduce the need for an iBGP mesh. But the end result we'll see in the design, there are other implications, but the end result of the design is the same when you do confederation versus route reflection. Now, in the case of eBGP, it gets a little bit more complicated. We're going to use one of the attributes in the actual update, which is the autonomous system path, in order to prevent the loops of routes going out one AS and then coming back in. Now, we will see that there are cases where I will advertise a route to my ISP, and if I have an alternate link to them, they will send the same advertisement back in. This is what the AS path is used for in terms of loop prevention in order to stop that case. To make sure that when my advertisement goes out, if it loops back around, I'm going to deny it when it comes back in. There are cases where the ISP is going to filter this out. There are cases where I need to filter this in. It depends on the specific version of code, depends on the platform and how they implement it. But the main idea is that normally you would either not advertise a route to a neighbor that has the same AS in the path already, or you would filter this as an inbound update. We'll talk about this later in terms of optimizations of BGP. It is less optimal to filter this inbound. It is more optimal to filter this outbound. And in the case of, I believe in iOS XR and NXOS, they do the default filter out. Because the basic idea is that, let's say we have some path X, and it has your AS in it. I give it to you, you have to filter it out. Okay, we agree that we're not doing any other exceptions to the design, so under normal cases, you cannot accept a route that has your own AS in the path. So why do I even advertise it to you? Because I know that you're going to have to filter it out. It's a waste of control plane cycles. So there's 2 options. Either I can give it to you and you can filter it in, or I could just filter it out to begin with, never send you the update. So both ways are implemented. It depends on what platform and what particular code you're looking at, but the end result is the same, is that you don't accept routes that have your own autonomous system in the path. Now, we will see that there are some exceptions for this, where you could use the allow ASIN command, or you could use the AS override. AS override is generally used in MPLS L3 VPN designs, where a customer is attached to the provider with the same AS number multiple times. So, for example, let's say that we have, from a very high-level overview, let's say we have the MPLS provider in the middle, and let's assume that they are AS1. Okay, then we have 2 different sites. We have a customer edge router 1 that's peering with them, and then we have another site that is customer edge router 2. But maybe we own our address space. So we already have a public AS that we want to use in order to route to the provider. Let's assume that this is AS 1234. Okay, this is our public AS, and we have address space that we actually own for this. So CE1, it does an eBGP peering to the provider. Inside the provider network, we don't really need to know the details, but basically what happens is that their edge router somehow is going to advertise the route to the other edge. Specifically, this is going to be used inside of a VPN v4 BGP peering. So we'll talk about that later. But the end result is that the route goes out that way. So if we were to say that the prefix is X, when X gets to the other side, the AS path is going to say 1, 1, 2, 3, 4. What's the issue with this? Well, the issue is that CE2's local process is AS 1, 2, 3, 4. So it's not able to accept the update in. Now, as basically a hack on the process as a workaround, they said, well, we know that this is the case, but yet we're not looping the traffic because everyone is centrally peering with the MPLS provider. They're doing loop prevention internally. And we'll talk about later how exactly that happens, but it does happen. So the loop is not there. It's just that the BGP process doesn't know it. So why don't we just take the AS number, we'll delete it, and we'll replace it with our own. This is what AS override means. So when the service provider peers eBGP to the MPLS L3 VPN customer, they typically override their own AS and replace it with the service providers. So then this fixes the problem with the loop prevention, but it's also going to complicate the design. So we'll see in later cases, there might be some situations where you can cause a loop if you override the AS and you have multiple connections to the individual customer. And that's where the feature called the BGP site of origin, or the SOO, is going to come in. It's basically like a tag value that we can use to prevent loops, just like we use the tag value in redistribution. Okay, so the third thing then is different, is the next hop value. So again, we talked about what are the rules in the peerings. There's a difference in the time to live value. What's the rules on the loop prevention? In iBGP, we just don't advertise routes that we learn from iBGP neighbors. If we do want to advertise them, we either need to do route reflection or we need to do confederation. The other option is just to peer everybody together as a full mesh. Now, the next big thing that changes between iBGP and eBGP is what is the next hop value that I advertise in the update. This particular value is, as we'll see, one of the most important functions of BGP. And the reason why is that BGP, again, is not a routing protocol. It is an application. The goal of the application is to exchange the application data, which is the network layer reachability information, the NLRI. So in other words, BGP is advertising the route details, but it's not advertising the path details. If we look at the specific route, what it actually contains is mainly three things that we care about. And in this case, we're talking about IPv4 unicast. So it includes the prefix and its length, so the route 1234/32. It includes the attributes, like what's the local preference, what's the AS path, what's the MED, and then it also includes the next hop value. Now, the next hop value here is very important because this is what IGP uses in its route recursion process in order to actually find the outgoing interface. If IGP is unable to perform this route recursion, the BGP route cannot be used. Now, we'll see that there are cases for this, that if you advertise a route in BGP, but for some reason you cannot reach the next hop, the route cannot be installed in the routing table and it cannot be advertised. But the reason that we even care about this to begin with is that different types of peerings have different next hop processing rules. So when we make the decision to peer between the loopbacks or peer between the connected interface, that does have an implication of ultimately the traffic flow. Because when I advertise you a route, and if you are peering to my loopback, I'm going to say in the update, the next hop is the loopback. This means when you actually go to route the traffic, your IGP is going to have to figure out how do we route to Brian's loopback in order to get to the destination. And that ultimately controls the forwarding. Now, there's a difference here, though, whether we're talking about iBGP versus eBGP. And in iBGP next hop processing, when you receive an update and you continue to forward it on, you do not modify the next hop value. We'll see that there is a specific reason why this is the case, and it has to do with route reflection, where a route reflector normally does not want to be in the data plane of the network. It is supposed to be a box that hosts the control plane. So for example, let's say that we have this particular network that's all one AS. So we have everybody running BGP everywhere, and then we have our exit point. So let's say that the exit point is out to router 9 and the exit point is out to router 10. So these are our external neighbors, but everybody else is all in one AS. Now, assuming that we're not doing any other type of tunneling, so we're not running MPLS, we're not doing GRE tunnels or anything like that, we're doing just normal global routing. The issue is going to be that if I want to transit a packet between these two eBGP neighbors, so let's say that a packet comes in from 9 and it's trying to get out to 10. This means that every device in the middle is going to have a route to it, right? So the packet comes into 7. 7 is going to need to know that the packet needs to leave via 10, but the route recursion would need to point towards 6, or it would point towards 3, because 7 and 8 are not directly connected. Now, what this means from a next hop advertisement point of view, let's also assume that in the iBGP network, we chose router 4 as our route reflector. So everyone peers with 4. It's going to cut down on just the number of control plane sessions that we need to maintain, but it's going to be at the expense of the detailed view of the topology. So again, we'll talk about this in more detail later, but there are advantages of using route reflection and there are disadvantages. The advantage is that it cuts down on the control plane load, but the disadvantage is that we lose visibility in the network, that we don't know about all egress paths, because the route reflector is going to choose one best path and then advertise that on to everybody else. But outside of that case, let's assume router 4 does know the routes and it's going to advertise it on. So the route comes in from 10 to 8. 8 sends it to the route reflector. The route reflector reflects it to router 7. And what does it not do? It does not change the next hop value. What this means is that when we actually go to forward the traffic will not go through router 4, because router 4 is only in the control plane. It's not in the data plane. So if router 9 does a trace to router 10, it would follow a path something like this, where it goes maybe from 7 to 3, and then 3 over the DMVPN to 5, 5 to 8, and then out. But router 4 is not going to be needed to be used for the actual packet forwarding. Now, in most service provider designs, this is the common case, that you don't want the route reflector in the data plane path because it's too fragile. There's 500,000 routes in the table and you have multiple views. So this is going to be some sort of box like ASR 1006 or something that has a lot of memory but doesn't really need to forward. So you could buy just the route processor, but you don't need the line cards. You need just a basic interface to plug in and form a peering, because they're not going to be used for the actual routing of traffic. And this is the key point to understand of why iBGP does not modify the next hop value, because IGP is in charge of routing the traffic. BGP is not in charge. Now, we can actually modify this if we want, and we'll talk about some cases later where you might need to modify the next hop in order to force the traffic to go a specific way, where this would either be with the neighbor next hop self command. We could use the set IP next hop under a route map, or in new versions there is a next hop self all, which forces the route reflector to be in the data plane. Okay, this is used in something relatively new called a unified MPLS design. This is for very large-scale service providers that they can't run flat OSPF Area 0 everywhere, or they can't run flat ISIS level 2 everywhere because there's too many routers. So to scale it, one of the applications is to use BGP. But outside of that case, normally you don't modify the next hop in iBGP purposely because you don't want the route reflector to be in the data plane. Okay, also there are some other implications that we'll talk about this. One of them specifically is BGP next hop tracking, BGP NHT. And if you change the next hop, it means that you can lose fast convergence inside of BGP. So we'll talk about that separately when we talk about optimizations, but from a very high-level point of view, the case that would happen is that when router 9 advertises the eBGP update to router 7, and router 7 sends this in. Let's say it sends it to the reflector sends it down, and then it goes out to the destination. By default, what is the next hop value that router 7 is going to advertise to router 4? So in this specific advertisement, when router 4 actually receives the update in, what is the next hop value that it's going to see? It's going to be this interface. Why is it going to be that interface? Because we're assuming that 7 and 9, they're eBGP peers, right? So they're normally going to peer on a directly connected link. There's only one path between them, so it doesn't make sense to peer via another path. So router 9 is advertising the route, and it's saying the next hop is me. The next hop is 79.9. 7 takes this route, and it advertises it to the iBGP neighbor, and it does not change the next hop. This means that when 4 reflects it on, it reflects it now to 8. 8 says, in order to route to the destination, I have to perform recursion to this next hop. Now let's also assume that we are running OSPF in the network and that we have tuned OSPF for fast convergence. So we've configured OSPF loop-free alternate, we have bidirectional forwarding detection, we have low SPF timers. Whatever the values are, assume that OSPF is converging sub-second. So if any link flaps in the network reconverges in 1 second, and it fails around the issue. Now let's say that the link between router 7 and router 9 goes down. So 7 and 9, this goes down. What is this going to cause to happen from an IGP point of view? Well, it really depends. Is the link between the providers advertised into the IGP or not? Now, in the case that router 7 is not updating the next hop, that link would need to be advertised. Because in order for router 8 to perform recursion to it, it has to have a route. And again, this is that separation. BGP is not a routing protocol, it's an application. IGP is the one that routes the traffic. So let's assume that we did not change the next hop value, which means that router 7 needed to either do redistribute connected or it needed to issue the OSPF command at the link level in order to advertise that into the topology. Okay, next the link fails. If the link fails, what is router 7 going to signal inside of OSPF? It's going to signal a withdraw, correct? And the way it specifically does this is to reflood the LSA, and it sets the maximum age. It's telling the other routers that I lost my connection to gig 1.79. Now, if this convergence is happening quickly, we're assuming that this is happening sub-second, and we have not changed the next hop value, it now means that BGP convergence is a function of IGP convergence. Because BGP is tracking the next hop to say, if the next hop goes away, I have to delete the route. And this is really the case of why you do not want to change the next hop. So it is a good idea to actually advertise those inter-provider links into your own IGP and not change the next hop value when you send it either to your internal reflector or between the edge routers. Now, we'll look at the actual case of this later, and I'll show an example of what actually happens if you do or do not change the next hop, and if you do or do not have next hop tracking on. The issue is going to be the difference between sub-second convergence and 3 minutes of convergence. So it can be a big deal whether you're hiding the topology details by modifying the next hop value. So again here, the default behavior is that you don't change the next hop for iBGP. You can if you want. You could say next hop self, you can manually set it in a route map, or we have this next hop self all in the newer code. Now for the eBGP neighbors, we do change the next hop. Because we're assuming that if I'm advertising the route to you, and we're external peers, you don't know the details of my internal topology. So I cannot tell you route to Bob in order to get there, because you don't know who Bob is. So I have to give you the route and say the next hop is me. Okay, that's the default behavior. Now there are some very corner case situations though where you might not want to change the next hop. So you could send the route to an eBGP neighbor and set the next hop to someone else, or to say that the next hop is unchanged. This is called third-party next hop. Now, we actually saw an example of this in the case of DMVPN Phase 2 with EIGRP and with OSPF. The case was that the spoke routers advertised a route to the hub and the hub was reflecting it back down, whether this was from disabling split horizon and EIGRP or whether we were using OSPF network type broadcast. The end result of this, remember, was that when the routers advertised the routes up to the hub and the hub advertised them back down, router 2 would say, to get to router 4, I need to use the address of this link in order to get there. That's what third-party next hop means. It means that router 5 is doing the advertisement, but it's not in the data plane. Route the traffic lead directly over the spoke-to-spoke tunnel to get there. So if we were to do eBGP and run eBGP over DMVPN, in order to enforce Phase 2, we would have to do next hop unchanged. So that when 4 sends an update to 5 and 5 advertises it as an eBGP route to 2, or to router 2 in this case, it would say next hop unchanged, or to manually set the next hop with a route map and then point it to whoever the remote spoke is. So there's very limited application of this. The normal legit application of this is for inter-AS MPLS layer 3 VPNs, which is definitely outside of our scope. So there are some very, very limited corner cases where you might want to do this, but under normal situations, the eBGP neighbor should just set the next hop to itself, because that's what you actually want to route to. Now, there is another very important thing to think about this, though. So let's say in our particular case, we have the network configured where router 4 and router 5 are peering eBGP, and they're peering over the loopbacks. Now, they learned the loopbacks to begin with because I turned EIGRP on all the interfaces. Normally, you don't do this. You normally don't run an IGP between providers. Maybe in some cases like MPLS Layer 3 VPN, but you're not exchanging the internal routes. In that case, the customer is exchanging its own routes to the provider. So this is kind of a weird corner case. Now, within the case of the CCI lab, this is definitely valid to say that you're running both IGP and eBGP between the neighbors, and the reason why they might do this is because it's a problem design. So let's think about it like this. Router 4 and router 5 are currently peering. We see this with the show IPBGP summary, and it says that we have the peer up to 150.155. Okay, let's now say that we do an advertisement. So on router 5, we do this. We show IP route connected, and we have this prefix 155.150/24. It's some connected link. So we're going to go to the BGP process, and we're going to simply say network 155.150 with a mask of /24. This originates the network advertisement. Now, as I was talking about before in IGPs, this is the key distinction in the network statement. This actually means originate the prefix 155.150/24. It does not mean enable BGP on the link, because again, BGP does not run on a link-by-link basis. It runs as a TCP connection to the neighbors. So that's why, in reality, the iOS team, they should have put this as two different commands. This should be like NLRI, whatever, and then whatever you're advertising. Because it's kind of confusing that the syntax is the same, but they mean two unrelated things in IGP versus BGP. Okay, next let's look at router 4. If we look at the show IPBGP summary, we see that we're learning one route. Okay, that's what the one over here is, prefixes received. Next, let's look at the BGP table. If we show IPBGP, we're learning the particular prefix. The field that we're looking for here is this greater than sign. This means that the route was chosen as a best route, which means that it can actually go from the BGP rib, which the BGP rib is the BGP table, to the global rib, which is the routing table, and then the routing table can push it down to either the software fib or the hardware fib, depending on what the platform is. Because again, these two control how we actually forward traffic. This one is just for software. Okay, now somebody had a question here. This is actually a really good question, and this is what the design problem is. The question was, why was there no rib failure? So think about it here. What type of peer are router 4 and router 5 here? Are they eBGP or are they iBGP peers? We should be able to tell based on this output right here. If this route was learned from an iBGP neighbor, we would have the internal status code right there. Since the internal status code is not there, it tells us it's coming from an eBGP neighbor. Okay, so the peer is eBGP. What is the administrative distance of eBGP? It's 20, right? So let's look at the routing table. If we show IP route 155.150, we're installing this as an eBGP route with a distance of 20. It says that in order to forward to the destination, you need to use the next hop 155.155. But notice what is not in here. The BGP process doesn't know the egress interface. It doesn't know that router 4 and router 5 are actually connected on multiple links, because that's not BGP's job. It's not a routing protocol. Its only job is to give you this information, and then it's up to IGP to actually route the traffic. So now we have to go through another recursive step. We need to figure out, how do we actually route to get to 151.55, the next hop? The next hop is reachable via multiple links, gig 1.100 and gig 1.45. So this means via the recursive property that this route points to this route points to this. It means that this route implicitly points to those. And we can see this in the fib. If we show IPsec for 155.155, it shows the egress interfaces. So this always shows you the final recursion. Okay, now let's go ahead and send a packet to it. Let's say we ping 155.155 and we source this from our loopback. Great, we can get there. Okay, if we do a trace route, we should see that it's ECMP. That some of the packets go to one link, some of the packets go to the other link. Okay, up to this point, there's no problem. And we saw that with the next hop value that's being used is the loopback, because that's what the peering address is. Okay, again, they're peering eBGP, and they're learning those loopbacks through EIGRP. We saw that if we look at the regular just show IP route, we see that we have a bunch of EIGRP routes. So we have these loopbacks, and then we should have the BGP route somewhere in here. One of the key differences you'll see in this output is that the BGP route doesn't show you the outgoing interface. Every other IGP route is pre-recursed in the Ceph table to the outgoing link. This is simply based on the fact that we're learning the routes on a link-by-link basis. So when router 4 runs EIGRP to 5, it runs it on a link. It doesn't run it on a multi-hop peering. So it knows that when I receive an update in gig 1.100, that would be my outgoing link. But BGP doesn't know that because it doesn't have visibility of the topology. And here is now the problem case. What we can essentially do in this particular design is cause a race condition of the BGP peering in which we cause an infinite recursive loop. And the way that we would do this, and let's look on router 4, let's say debug IP routing, is to go to the routing process of router 5 under BGP and to advertise the prefix that we're using as the peering address. So now on router 4, it's going to say, I now got a new update through eBGP. Specifically, this now has a closer administrative distance than my previously installed route. And it now says I'm going to use 150.1.5.5/32 via 150.1.5.5. This makes no sense. It's saying to get to 5, use 5. Then to get to 5, use 5. To get to 5, use 5. And you can see the routing process knows this. It says there's a recursion error. There's a loop. What do we do? The ultimate result is that we cannot install the route in the table, which means that the BGP peering is going to go down and it enters this race condition, where sometimes the peer will be up, sometimes the peer will be down, but we will never be able to forward traffic. Because when IGP goes to say, okay, I got the route from BGP, BGP told me the next hop is 150.155. I do the recursion, it points at another BGP route, which points back at the loopback. And this is really what the significance of the next hop is. That if for some reason you cannot properly recurse to it, you're not going to be able to use the route. Now, eventually the BGP peering will go down. And if we were to modify the administrative distance, as someone mentioned here, yes, that's a valid solution. Okay, the issue to begin with is that eBGP is a distance of 20 and eIGRP is a distance of 90. So when we have both equal longest matches, we choose the lower distance. We choose the BGP route. Now, if we want to advertise the route on through BGP, but route it through another protocol, that is a valid case. Because BGP is not distance vector, it's path vector. The rules work differently. So we could solve this by doing this. We could go under router 4's process and say that the distance for BGP external is 91, and internal, let's leave that as the default, as 200. And the distance for local routes, that doesn't matter. Let's say 1. And if we now show IP route 150.155, now it's installed via eIGRP. If we show IP BGP 150.155, we're getting the route, but it says you have a routing information-based failure or a RIB failure. What this means is that you have the route, you ran the best path selection on it and it was fine, but for some reason it didn't get installed in the routing table. Okay, normally that means it's because you have another route that has a lower administrative distance, which is the case here because I made eBGP higher than eIGRP. Now eIGRP gets installed and then we can't use the BGP update. Now it is okay in certain situations to do this though, because let's say now we get the route and we advertise it to router 1. And if this is an iBGP peering, let's look at this. And this is actually going to be a really interesting case here to add router 1 to the case. Let's go to router 1 and now say router BGP 4, neighbor 151.44, remote AS4. The update source, oops, that should say 4. And the update source is the loopback. And on router 4, we need to do the same thing. So let's say router BGP4, neighbor 150.111, remote AS4. And the update source is the loopback. Okay, the peer comes up. If we show IPBGP, we should get the route, which the route in this case is 155.150. And if we, let's do this. How would we need to do this? We would need to, let me go to router 5. I need to make a change on 5. I need to say on 5 that eIGRP is enabled on this link and the loopback, but not on that one. Because that one I want to advertise into eBGP only. Okay, right now on router 5, I have just a very broad network statement under eIGRP, which is everything. So actually, let me undo that on all the routers. Let's be a little bit more specific here. Because this works, but this is just bad practice to do that. So let's say no router eIGRP 1, and instead under eIGRP 1, we're going to advertise our transit links and our loopbacks. Okay, next on router 5, I'm going to say this, no network 155.100, and let's show IP route, no, show IP route local. I need to see what our, oh, it doesn't take local on this one? Let's do this then. Let's say do show IP interface brief, pipe exclude unassigned. Okay, I want to enable eIGRP on almost all of these links, basically. So I want to advertise just those ones in. Network, those, mask of all zeros. Someone commented, please use the new eIGRP syntax. I forgot about that. I will make a mental note to continue to do that throughout the rest of the class. So from now on, eIGRP is going to use the named format so we can see the difference in the syntax. Well, let's do this. No router eIGRP1, router eIGRP-A, address family IPv4 unicast autonomous system 1, and then the same syntax for the network statements. Okay, so the eIGRP neighbors are now up. Okay, this means that 5 can peer eBGP with 4 because they're learning their loopbacks through eIGRP. Then 4 is advertising the route on. The route that we are specifically talking about in this case is this gig link. It's 155.150/24. So 5 advertises it to 4, 4 advertises it to 1. This here is eBGP, this one is iBGP. When router 4 gets the route, if we show IPBGP 155.150, notice the next hop. Okay, the next hop is 5's loopback, because that's what they're peering with. Then we advertise the route to 1. 1 says show IPBGP, 151.550, no, 155.1.5. And it says the next hop is the same, 155.1.5.5. The router we learned the update from was router 4, who has a BGP router ID of 150.144. This is the peer address that we're actually using for the neighbor statement. This is the router ID that they have assigned. In this case, it's the same because I'm peering with the loopback, but technically these are 3 different fields in the update. The update shows you the next hop. It shows you who was the peer that it came from, which is basically the source of the IP packet, and then you have the router ID of the originator. Okay, we'll look at a little bit later what's the actual format of the update once we talk about NLRI origination. But the only thing that really matters in this case is that router 4 did not change the next hop value. So let's look at this from a forwarding point of view. When router 1 goes to route to show IP route 155.155, it says the next hop is 150.155. So I need to say show IP route 150.155. It says this is reachable via router 4, and actually I don't want to do that. I want to, why is it doing that? I need to say, here is the issue. Let's say the delay is high. Okay, basically the DMVPN is less preferred in this case. Okay, so let's say that. Okay, we're going to router 3. It doesn't matter as long as we're not going to 4. This means when I do the final recursion to the destination, 155.155, the data plane points me to someone who is different than the control plane advertisement was from. And this is the exact case of why BGP is not a routing protocol. I am giving you the route and telling you to use someone else to get there. How you connect the dots, it's up to you. If IGP was not behind the scenes here doing recursion to 5's loopback, none of this would work. So from router 1's point of view, if we now say trace 155.155, the packet doesn't go to router 4. Now, why router 3 doesn't have the route, I don't exactly know here. Let's look at router 3. And, well, actually, router 3 is not running BGP is what the issue is. But let's do this. Then I need to, let me just shut that other interface down. Okay, and actually, this is another interesting case that we'll talk about. What happens if your IGP recurses to a router that's not running BGP? That's why you have to have the full iBGP mesh. There are other solutions for that. We'll look at using MPLS as a solution. We'll look at using tunnels as a solution, like we could tunnel BGP over GRE, and then we would have the same end result as MPLS. But basically, you just need to make sure that someone has the route in order to actually get there. So let's now say show IPsef for 150.155, now 155. Too many 5s in this output. Okay, now it's going to router 4 again. Why is the DMVPN not up? Let's say show DMVPN. I am registered. Show IP eIGRP neighbors. I'm not adjacent on the tunnel. Why am I not adjacent on the tunnel? Let's look at this on 5. Actually, first on 1. let's say show IP eIGRP interfaces. The tunnel is enabled, but there's no neighbors. Let's see on 5, show IP eIGRP interfaces. It's not on the tunnel. That's what the problem is. Let's say show run section eIGRP. I missed a network statement. Address family IPv4 AS1. Okay, remember this is the shortcut here. This is not documented in the parser, but it takes it. The full syntax is address family IPv4 unicast autonomous system 1. I just said address family. You could also, I think you can also say this, address family IPAS1. No, it has to be v4. Because also v6 is a keyword there. I need to say network 155.1.0.5. That's the DMVPN. Okay, now the tunnel's up. So now from one's point of view, if we look at the Ceph table, it should say we need to recurse to the tunnel. And if we trace, we see the packets get there, but they don't have to go through router 4. So again, this is the whole logic of why the next hop is so important to BGP. That there are many cases, well, I will advertise you the route, but tell you to go to someone else in order to get there. And then it's up to you to look at your IGP, to look at your static routing, to look at your MPLS tunnels in order to figure out how do I actually route to that destination. So the takeaway from this is that when you're building the initial BGP network, the peering addresses do matter. Because for eBGP neighbors, those will be the next hops. If you're sourcing it from the loopback, it means the next hop is the loopback. If you're sourcing it from the interface, the next hop is the interface. But in either case, you can always modify this later if you needed to. So you can do it manually with a route map. You can do it with the next hop unchanged in the case of eBGP, or you could do it with the next hop self in the case of iBGP. So again, we will go over these cases, but this is the fundamental logic that you have to hammer into your brain here for BGP, that it is not a routing protocol. If recursion is not there to the underlying transport, none of this is going to work. So now once we start to get into the more complicated things of BGP, you have to assume that all this stuff underneath is working. Otherwise, you'll be troubleshooting a problem in path selection, and it doesn't have anything to do with BGP. It's something that's wrong in your IGP routing or something wrong with your layer 2 network. So when we're building the networks in layers, starting from the bottom up, this is the most important thing to think about in BGP is how is the next hop being calculated, and then ultimately how are we routing traffic to that next hop. Okay, there's some questions here. And Eugene, can you actually do that? I did not know you could do that. Let me try that. Let's say this. No router eIGRP-A. Router eIGRP-A. Network 0000 under the address family. Address family IPv4 AS1. Network 0. AF interface, let's say tunnel 0. Shutdown? I did not know you could do that. That is very useful. Thank you, Eugene. So this would actually have been quicker for me to do, because you can basically remove the link under the eIGRP process. So it is kind of sloppy syntax to do this though. So I'm saying enable the process everywhere, but then I'm disabling it on the particular interface, which means it's still mapped it's still matched on a network statement. So when I do an origination, I'm still going to be trying to run the eIGRP control plane on there. If you say no shutdown, then it's going to come up. But this is basically then withdrawing it from being able to form an adjacency on that link. There's a question, the network backdoor. We'll talk about that later. The backdoor network in this case would not have an effect, I do not believe. I'll have to double check on that. So let me come back to that a little bit later. We'll talk about what the backdoor route actually means. There's a question, sometime on edge routers, we do an aggregate address for eBGP and next hop self on the internal routers. Is that I'm sorry, is that a question or a statement? Sometime on edge routers, we do an aggregate address for eBGP and next hop self on iBGP internal routers. Yes, you can do that. That's fine. So is what you're asking, can you do, so let's assume that this is the external network. So you peer to your edge, so our edge is router 7, and then this is our IBGP network. So you get the routes in, so let's say you have A1, A2, and A3, and then you're aggregating these just to A. When you do the aggregation, the next hop does also become an issue. So I'm going to come back to this specific case later. The question becomes, when you do the aggregate, where do you get the next hop from? Because what if the subnets of the aggregate are coming from multiple different peers? You can't seed multiple next hops in there, so which one do you do? Well, the question is, who's the originator? If I am the originator, I'm the next hop. So in this case, you wouldn't even need to do next hop self, because if you are locally originating the route, then you are going to be the source of it from a next hop point of view. But we're going to spend a lot of time on aggregation in BGP. There are so many features in BGP for policy application. There are literally 1,000 different ways or more that you can accomplish the same exact goal in BGP by doing different options. So we need to think about, if we have just a very vague question that says, do this is our end goal, you need to think about what are all the different ways that you can do that, because if you get to the exam and they say don't do X, Y, and Z, you need to know that A, B, C, D, E, F, G are still the leftover options that are available. And we'll see from an exam grading point of view, this means that 99% of the time in the case of BGP, they're going to have to grade you on the results, because there are simply too many variables that would come into play when they're trying to grade you based on the config. Okay, there's a question, when we initiate a BGP peering session, what is the reason that we are asked to remove the default IPv4 BGP address family? Now, in most cases, and what we saw here, we established a peering between two neighbors, and we saw that they automatically negotiated the IPv4 unicast address family, which is AFI1, SAFI1. Okay, that's the default value. It's normal BGP routing. Okay, that's on by default in iOS. They're assuming that if you run BGP, you're probably running it for internet routing. But on other platforms, that's not the default. Like in iOS XR, nothing is on by default. You have to turn it on. And the reason why is that you might not be using BGP for unicast routing. Maybe you're using it just for MPLS routing, or maybe you're using it just for IPv6 routing. So in that case, you might not want the peers to automatically negotiate regular IPv4 routing. So there's basically two ways to do this. If we show run section BGP, we could do this. We could say router BGP5, no BGP default IPv4 unicast. Okay, what this command says is that when I go to establish a BGP peering, do not automatically tell them that I want to run unicast routing. Now notice what it did here when I issued the command. It changed the format of the syntax under the BGP process. It automatically generated the address family IPv4, and it automatically said that this neighbor was activated. Or in other words, when I send the capabilities exchange, I want to tell this particular neighbor that I support AFI1, SAFI1, which is IPv4, and they don't show it here, but it's actually IPv4 unicast. Now let's say I have a new peer that comes on. I go globally and I say neighbor 1234, and their AS is whatever, 1234. This means that when I do the capabilities exchange, I will not tell them that I have AFI1, SAFI1. Now I can turn it on if I want to. It's just that the default behavior has now changed. That I would need to go under address family IPv4 unicast and say this neighbor is activated. So the end result is the same. It just depends on, do you want to activate everyone by default, or do you want to individually activate them? Because think of it this way. Let's say we have 999 peers that run MPLS VPNv4, and we have one peer that runs IPv4. In that case, from just a manageability of the config, it would make more sense to turn off the default IPv4 unicast and then say for this one peer, you're on. But let's think about the opposite. Now you have 99 peers that are running IPv4, you have one peer that's running MPLS. You would say, leave the default activation on for the 99, and then I will deactivate this one specific neighbor. And the way that you would do that would be just to go under the process here, go under the address family, and then issue their neighbor statement, but put a no before this. So you would say no neighbor activate, and it says when I do the capabilities exchange, don't allow, don't tell them that I actually want to use that. Okay, there's a question here. What's the difference between passive interface and AF interface shutdown? A passive interface means that you will not send hellos, but you'll still originate that prefix in the topology. So what I did here by shutting it down under the AF, and this is for EIGRP, this is not for BGP. If we show run section EIGRP, which was, no, where was it? Oh, here. Let's say show IP EIGRP topology. Well, that's not a good example. I would need to say, let's say this, router EIGRP A, address family IPv4 AS1, AF interface tunnel 0, no shut, AF interface loopback 0. No, let's say gig 1.5, shut. Okay, if we show run interface gig 1.5, okay, we see the prefix. The prefix is 155.150/24. Okay, which we have it. Okay, next we're going to look at the EIGRP topology. Show IP EIGRP topology for 155.150/24. It's not in there. Okay, this is different than doing this. If we go under EIGRP A, and we say, let's say, do show run section EIGRP. Let's say EIGRP A, let's go to the AF, and we'll say passive, but we'll say no shut. Then show run section EIGRP. The difference now is that the link is in the topology, but I'm not sending hellos, so I would not establish an adjacency. This is the typical case that you do down to the access layer. So let's say you have Catalyst 6509 as your default gateway for your end clients. You would want to put a passive interface on those VLAN interfaces because you don't want to send EIGRP hellos down to the end host. So it's inefficient for the control plane, but worse than that, it's a security issue. Because someone could capture your frames and then either do injection, like send an EIGRP packet back in, or figure out the topology by looking at the updates. It's just bad practice in general to send control plane frames down to the access layer. So that's what passive interface is doing, is just saying that you don't want to send hellos, but you can still advertise the route into the topology.